Hey, welcome back. So Google have released their first open weight models this week, specifically the Gemma 7 billion parameter model and the Gemma 2 billion parameter models. Now we can argue amongst ourselves whether those models are better or worse than Mistral, but actually that's not what makes those models interesting. What makes those models interesting is they share their tokenizer with the Gemini model. And that reveals a whole lot about Gemini. And in fact, the way that Gemma handles tokenization and handles vocabulary is massively different from both how Mistral and even GPT-4 handles it. And in this video, I'm going to show you the how, why, and where the Gemini tokenizer is different from the Mistral and the GPT-4 tokenizers. And we're going to do that by running some benchmarks against them. And oh boy, is it interesting. But before we deep dive into Tokenizer, we're going to take a quick look at some of the outputs from the Gemma model. So the first thing I'm going to do is I'm going to run the Gemma 7B model on my machine using Ollama. I have a whole video on how you can get started with Ollama. So I will just type in Ollama run at Gemma 7B. And as you can see, I'm started. And I'm going to use my favorite test, which is who is Ada Lovelace. And as you see, that is going to come back saying that she was an English mathematician and pioneer in coding, considered one of the first programmers, etc. And again, that's a fairly decent response. I will also run a test of who is Katy Perry. And you can see it comes back with Katy Perry is a popular American singer, born in 1985, known for catchy music, blah, blah, blah. I don't think that's the best description in the world. I actually much prefer what comes back from Mistral, but that's more of a kind of personal preference there. Of course, it is pretty good at math as well, so I will ask it something like, what's 25 multiplied by 2 plus 4 multiplied by 3? And there you go, it's going to come back with the answer. What's cool about this answer is you can see it's actually respecting PEMDAS there. So it's doing the multiplication first and then doing the addition to get the answer. So as you can see, if I run the same question with something like Mistral, I don't actually prefer the answer. Although it's got it right with 62, I don't like the verbosity of the answer. And actually, if I then start making the questions a little bit more complicated with Mistral, it gets confused and it doesn't come back with the right answer. However, if I ask something like who is Katy Perry, for example, you're going to see it's going to come back with a much better answer than the other one. So you see it's more accurate, comes back with 1984. It tells you about I Kiss a Girl being the first song, etc. And then lists a few of her other songs and talks about American Idol. So in this case, I think the Mistral answer is much, much better. But this isn't a video about comparing the outputs of Mistral to the outputs of Gemma. This is a video about the tokenization of Gemini. But I really just wanted to get you comfortable with asking the sort of queries that you may ask Gemma or Mistral. So with that, I want to come back into tokenization for a second. So in one of my earlier videos, I created this reference model of how a large language model works. So if you look at the bottom there, you see the question, who is Ada Lovelace? And that is our input text. The large language model never ever sees the words, who is Ada Lovelace? It only sees tokens. And in order to get those tokens, it is run through a tokenizer. So in this case, for the Gemma model, it is using the same tokenizer as Gemini. So it's using the Gemini tokenizer. So when you run who is Ada Lovelace through that, it's going to come back with a set of numbers that relate to the phrase who is Ada Lovelace. And generally, that will either go to a word or a subword level. So you see in this case, who is Ada Lovelace comes back as 111643338, blah, 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 blah. And then that is what is passed to the large language model. And then at the other end, when you get the output, Ada Lovelace is blah, then it's not returning the English text, it's returning the tokenized version of that. So you see those numbers. So again, if I take that same phrase, who is Ada Lovelace, you can see it comes back, who is 1164, is 338, Ada is 23255, LOV is 23974, EL is 295, and ACE is 815, and question mark is 29973. Now, this isn't Gemini or Gemma's tokenizer. This is actually the Llama tokenizer. In fact, it's specifically the Llama 2 one. But it's to give you this idea of breaking up words and subwords. Now, one of the challenges that large language models have is that when we start looking at various languages, then there's far too many words available in the dictionary. So something like the Finnish language has something like 800,000 words, and Swedish has 600,000 words, and even English has 270,000 words. So to hold every word in the dictionary is probably just too much. It would bust the vocabulary in general. So what most large language model creators do is actually try and have a smaller vocabulary and then use tokens as subwords and then combine the tokens together to make a full word, which is why in the Ada Lovelace example, the LOV, the EL, and the ACE is actually 3 different tokens as opposed to 1 token representing Lovelace. But more common words such as who or Ada will actually get an entire token to themselves. And that is the really trade-offs of tokenization. Now, one of the things and one of the problems that you see with most tokenizers, they're very biased towards English language because that's where most of the frequent text of the training of these large language models are. So if I'm interacting with a model in another language, whether it's something like Maori or Welsh or something, I'm going to be paying a penalty for not using the English language, and that penalty is it's going to be a higher amount of tokens. And it's not just the English language, it could be things like emojis, it could be things like Morse code, etc. So the trick is to be able to have a more representative vocabulary, but at the same time trade off that sizing. Now, what's interesting about the Gemini and Gemma tokenizer is they've taken a completely different approach to what GPT-4 or Mistral has. And I'm going to show you that in a second. But before I do that, I want to compare the sizing of the vocabularies versus some of the major tokenizers. So if we look at the Mistral model that I showed you earlier, it's actually got a really small vocabulary. In this case, it's 32,000 tokens. And in fact, it uses the same tokenizer as Llama. In fact, they have the same vocabulary size, and if you want to see us doing a bit of a mix and match, you can see that in one of my other videos. But they have the same tokenizer. Now, they actually have different token dictionaries, different vocabularies, but you can see they're both at 32,000. Another popular one used by things like Pythia and others is the GPT Neo X, and that's got 50,000 tokens. Whereas GPT-4, the big model of all at the moment, it has got 100,000 tokens. And again, I've got a whole video breaking down GPT-4's tokenizer, which is called TikToken, and you can go into the more details of that. But if you look at Gemini and Gemma, it's got a massive vocabulary. It's 256,000 tokens. That is a huge vocabulary. It's absolutely massive. And there is an impact of that, which is in the embeddings layer. So if I come back into my reference model, one of the things that we're going to do in another video is break down how the embeddings layer works. But this embeddings layer has got a massive matrix of vocabulary tokens to vectors. So in fact, every vocabulary token would be represented by an index in that array. So the bigger the vocabulary, the larger the embeddings layer is going to be. And you're probably wondering yourself, well, what does that matter? Well, if I look at the underlying models for a second, we all know the Gemini 7 billion parameter model is a 7 billion parameter model. But if I do the calculation of the vocab, so in this case 256,000, multiplied by the number of dimensions, so dimensions in this case is the vectors, which tells you the closeness of the words to each other. Again, don't worry about that too much just now. We will do a whole video on that at some point. You will see that in the case of Gemma 7b, that means 11% of the entire model is taken up by the embeddings layer. Whereas if I look at something like the Mistral model, which has got a smaller vocabulary at 32,000, then it's got a slightly higher number of dimensions, i.e. vectors, 4096, but you can see it's only taking up 1.8% of the total model is embeddings. So the difference there is huge. It becomes even more noticeable when we come down into the smaller model. So Gemma 2b, for example, actually has an embeddings percentage of 26% of the entire model of the 2 billion parameters is actually the embeddings layer, right? Because it's got 524,000 parameters in that embeddings layer alone. And you can get that calculation by calculating the vocab, 256,000, by the number of dimensions. So you see that the Gemma 2B model has a smaller number of dimensions, less vectors, because it's a smaller model, 2048, which actually in some regards makes it somewhat of a miracle that the Gemma 2B model, considering 25% of it is actually just embeddings, is actually able to return a result at all. So now if I come back into Ollama and then I run something like Gemma 2B, for example, and I ask who is Katy Perry, I mean, remembering that this is 25% embeddings and only 75% is the other layers in the model, the fact that it's coming back with a fairly decent answer of who Katy Perry is really nothing short of impressive. And if I compare this to the sort of results that you're getting from something like Pythia or Tiny Llama, I mean, it is actually quite incredible that it's coming back with such a decent result. And I can actually do also who is Ada Lovelace, and I was going to come back with a fairly decent answer. It will hallucinate a little bit in this case, but, you know, that's not unrealistic for the fact that it is such a small model, but most of the model, or 25% of the model, is being taken up by embeddings. And as you say, Victorian mathematician and programmer, considered the mother of computer science. So it's, you know, Lovelace developed a programming language called Lavalier. So it's making some stuff up there, but you know, the fact that it's coming back with a vaguely nonsensical response honestly is a miracle in itself. So as you can imagine, Gemma is paying a penalty for having a huge vocabulary there, and that penalty it's paying is the number of attention layers and the dimensions that it can have, because it's got to satisfy that very, very large vocabulary. But of course, as you start scaling up the model from 2 billion parameters to 7 billion parameters, or up to however many parameters that Gemini has, that sort of penalty goes away on those larger models. So it's really an insight, not into what Gemma's doing. Gemma's uninteresting in this sense. The insight is what's happening on the Gemini side. And as you can imagine, that's going to be a little bit of the secret sauce that Gemini is doing. And the way Gemini is approaching this is really, really interesting. So what we're going to do now is actually run a benchmark that I created of some reference text across a whole different types of domains. And we will see how GPT-4, how Mistral, and how Gemma or Gemini will compare at a tokenization level only. And the results are absolutely interesting. So I'm going to run Python benchmark.py. I'm going to pass in my dataset JSON. I will show you what that looks like in a second. And as you can see, I'm going to compare Mistral AI, GPT-4, and Google Gemma 7b. And again, it's only looking at it a tokenization perspective. Now, if we take a look at the result here, you can see where I'm doing comparisons. So I have got file name, class, subclass, and the model and the results here. And basically the result is going to be how many tokens have came back for that particular text. So what you are going to start to see is when I start going through these categories, in this case I've got things like Pokemon, YouTubers, brands, rock bands, TV shows, etc. You are going to see that Gemma 7b with its massive vocabulary is actually outstripping GPT-4 in these cases, especially in things like pop stars. And what pop stars has is just a list of some of the more famous pop stars of today. Now this one's super interested. NFL players, 153 tokens for Mistral, but down at Gemma, 115. And again, it even beats GPT-4 in this case. Same with things like soccer teams. And again, when we look at things like Japanese, French, Maori, Cyrillic, again, this is where we get huge differences. GPT-4 in this case for Japanese is 488 versus 240 for Gemma. Again, lowest number is the better. Now, if we take something like Cyrillic, for example, GPT has got 526, but Gemma is only 276 tokens. So it's almost 50% more efficient. Again, even in programming, I would say this is where GPT does a better job than the Gemini model tokenization. GPT is actually way more efficient in general than Gemini is. Part of that is the way that Gemini does its tokenization, because actually it splits out the numbers all of the time. So GPT will maybe take the word 10 or 20 or the numbers 10, 20, 30 and treat it as one token. Whereas Gemma or Gemini will always split out each number individually as their own tokens. So just kind of be aware of that. But even then, with that in case, GPT wins all of the time. But again, Mistral is always got a higher token count than the Gemma model. Again, we see this again here with things like American presidents. Gemma's coming out on top. You see Hollywood stars. Gemma's coming out on top as well. Now, my particular favorite one is going to be emojis. So if we look at emojis here, Mistral 865 tokens, GPT 675, but Gemini 245 tokens. So you can start to understand how these different models are prioritizing tokens. Mistral isn't looking at things like cultural references or anything like that. It's just taking a corpus of text as a whole, and it's getting the most frequent words. It's got a little bit of focus on programming, but nowhere near as much as the GPT models. GPT has looked at some of the kind of cultural text. You can see it's tokenized things like American presidents and all that sort of thing. But things like multilingual languages, Japanese, Cyrillic, or also emojis, it's really not put a focus on that as well. And again, Gemini and Gemma is really focused on these multi-language, but also kind of cultural references. And I'm going to show you how that is visualized in a second. So Gemma and Gemini are really trying to focus down on representing not just most frequent words, but actual objects, cities, colors, famous books, famous people are all getting represented as much as possible as tokens and as single tokens where as possible. And that actually is going to really, really help it later on when it's trying to do combinations and give good answers back, as we're going to see. And don't worry, I'm going to release the benchmark data and all of that in my GitHub, and you can access it and run some of these tests yourselves. But if we were to look at what's actually in the benchmark for a second, you're going to see it's nothing that exciting. So if I go into something like language, there's a whole bunch of Cyrillic text. Here's some French text. Here's some Japanese text. Here's some Spanish, here's some Maori. It kind of makes sense. If I go into something like entertainment, you can see that's just a list of Pokemon characters. Pop stars are things like Madonna, Michael Jackson, Lady Gaga, Taylor Swift, Rihanna. You know, things that are probably not going to be considered as real words there. But, you know, if you tokenize heavily towards things like Aguilera or Timberlake or something like that, then you know that the model or the tokenizer is focusing on cultural references. And that's why I've got entertainment in there. And then it's the same for things like books, famous books, Harry Potter characters, Shakespeare books, etc. It's to give this sort of breadth. Same with things like movies and Disney characters. And again, in things like programming, you can kind of see C language, C++, and I'm extending out that list as we go. Or my particular favorite is things like NFL teams, Arizona Cardinals, Atlanta Falcons. You will probably see that in the Gemma model, nearly every single one of these is going to be one-to-one between tokens and words. So with that in mind, let's actually run a couple of examples and see what they look like. So in this case, I'm going to run through the NFL teams and we're going to compare how it actually tokenizes as well. And then we'll see if it's a sensible tokenization. So we're going to have 3 columns coming back. We're going to have the Mistral 7B column, GPT-4, and Gemma 7B. And you can kind of see here Arizona Cardinals. Mistral's sort of broken that into 2 words with Cardinals, but GPT-4 and Gemma 7B are just taking entire words. Same with Atlanta Falcons. And again, Mistral gets worse and worse and worse. GPT-4 has got split up B and Altamore, whereas Gemma straight Baltimore Ravens. Buffalo Bills, GPT-4 has done the same. And this is an incredible insight if you haven't figured this already. You can see GPT-4 is not treating NFL teams as entire tokens of themselves. They are going down to a subtoken level, whereas every single NFL team, every word is actually represented as a token. Every single one. The only difference here is 49ers, and that's because of the splitting numbers out as individual tokens is one of their generic rules, which means already you can see that Gemma and Gemini are prioritizing things and cultural references as opposed to using subtokens. Even GPT-4 is doing the split. And you can see the difference in size. There's Gemma 7b, stops at 108. GPT-4 continues on a bit, but Mistral goes down to sort of 180. And again, I can switch that from NFL teams and I can just put my sort of generic sports teams in here. We can run the exact same test again, and you can gonna see it's a similar result here. So New York Yankees, Manchester United, already Mistral is splitting up and splitting up and splitting up, but GPT-4 and Gemini are splitting, are sort of side by side all the way. Where it starts to get interesting is you see Gemini here, Bayern Munich. Bayern's an entire word, whereas in this particular case, GPT-4 is splitting it out. So again, Gemma is actually focusing on more worldly things as opposed to just English and kind of American. Again, further down, you see the same with Juventus here, and there's Juventus, representing a single token. Even things like Paris Saint-Germain, again, split up, individual token each one. Germain, in this case, even in GPT-4, split up into 3 tokens. But more importantly, these are the sort of tokens you would expect to see. You would expect to see Carolina Panthers as 2 tokens. You wouldn't want to see that split up into multiple tokens in that sense. So the Gemma and Gemini tokens, although it's a larger vocabulary, when you look at it, it makes sense. Now, again, if I move out of sports for a second and we go into something like American states, again, we're going to see a similar sort of thing here, right? So even GPT-4 is splitting up words like Alaska, right? It's 2 tokens in this case, but not Gemma 7b. Every single state here is being represented as either 1 or 2 tokens, is never splitting up subtokens anywhere. So again, it's taken that sort of Tennessee, again, is split up there, but Gemma never does this. It is focusing on things. And when I do the video on embeddings, I think you're going to understand why, but we're not going to discuss that on this video, but you kind of see what's going on here. Again, we'll run another test here. This time we're going to do movie stars. Similar sort of thing. Now, in this case, what you will see is Gemma and GPT-4 behave quite similarly. You see Denzel Washington is split up. Meryl Streep is split up. Nicole Kidman, 2 words, right? Jackie Chan. Penelope Cruz is split up there. Kate Blanchett. So again, some of the kind of non-American stars are getting split up there. But the more famous ones are certainly kind of remaining as entire tokens. But if I switch this away from being a kind of diverse set of movie stars and I move this to kind of more Hollywood stars, although things like Meryl Streep is still, and Denzel Washington are still split up into tokens, when we get to folks like Tom Hanks, Julia Roberts, Sandra Bullock, and even Leonardo DiCaprio, there's no scenario where DiCaprio is a common word unless you're looking at things like movies. It is taking a precedence. It is really biasing towards people and things so it can build up this world knowledge. And I think that is one of the big differences that we're seeing between Gemini and GPT-4 and certainly Mistral is Mistral and GPT are using the deeper layers to be able to make those joins, whereas Gemini and Gemma are really trying to get things as close as possible in the embeddings layer and have this idea of world knowledge, people knowledge, things knowledge. And you can kind of see that here with things like George Clooney, Nicole Kidman, Johnny Depp, Will Smith, Scarlett Johansson, Jennifer Lawrence. Again, all of these Hollywood stars. Reese Witherspoon is only 2 tokens, right? And again, if you look over here, it's just multiple tokens on even GPT-4. Don't even ask what's going on with Mistral there. So you see, there's such a fundamental difference. If we look at programming for a second, again, Mistral is pretty good, actually. It's got some of the keywords, things like const and CTX, the sort of common things that you would expect in common languages like TypeScript, for example. JavaScript is actually being tokenized into single words. So Mistral has done some optimization in programming languages. GPT-4 by far is the best for programming languages. It's really kind of got it nailed there. And it's the sort of optimizations that you would want. But actually, I don't think, although Gemini is not as efficient, it is the sort of words that you would want to be tokenized correctly. So there's import URL encoded from body parser, canvas const, set timeout is an entire token as you would want in a kind of JavaScript based language. Canvas, fill style. So there is definitely a focus towards programming languages, but it is a reasonable tokenization. But in this case, I would say the GPT-4 is just a little bit more efficient. But I think they are pretty good tokenizations. I'm a little bit disappointed that Chris Hay UK is not an entire token in itself. Maybe that's an aspiration for this channel, is for that word to become one token. But either way, as you see, GPT-4 does do better there. And I think that's because GPT-4 has really sort of optimized towards programming languages, whereas Gemini is focusing between culture, languages, geography, things. And again, we can see this if we come back in and maybe run this against some languages. And in this case, I'm going to run it as Cyrillic. And the differences between Mistral and GPT for things like the Cyrillic language, it's not even a comparison. You kind of see Mistral is just like subtoken, subtoken, subtoken. GPT-4, similar subtoken, subtoken. But again, Gemma here is really, and Gemini is really picking up much larger tokens. It's got a much deeper understanding of the language. And you see here it stops short at 275, but GPT-4 and Mistral, it kind of keeps going. Mistral actually does a better job of tokenizing than GPT-4 does here. And again, similarly, if you look at something like Japanese, you see that Gemma is actually sort of doing multiple tokens at once, whereas GPT-4 is almost single tokens all the way. And then it's similar for Mistral. It's, so again, you start to see this focus from Google on kind of multiple languages. We'll move on from languages and we'll maybe look at something like emojis, for example. So we will run this. And again, it's a sort of high Unicode character base. Again, Mistral, Unicode, it's doing not too bad of a job here. GPT-4 has got itself in a bit of a tiz. But there you go, Gemma 7b, just absolutely nailing it. Token. It stops at 245 here. And GPT-4 and Mistral are all the way down to like 860 odd for Mistral or 6744 GPT. So Gemma and Gemini have focused on emojis. So they're wanting that kind of modern text there. And then I think the last one that we're going to run is just to sort of hit home this point about things. As we're going to run things, something like maybe cities, for example. So I'm going to change this to geography, and then we're going to put world cities, and then we'll run the exact same query. And then we're going to see a similar sort of thing, right? So there's Mistral, New York, GPT-4, New York, and then Gemma, New York. So that's okay. But straight away, as soon as we start getting to worldly cities, Gemini's got Tokyo is an entire token, but GPT-4 is already splitting up. And again, we put some of the sort of translated versions here. Gemini is just nailing it. There we go. Paris, Cairo, Moscow, even kind of Moscow in Russian there, nailing it. And again, as you look through this, it just kind of looks natural. It's sort of the tokenization that you would want from Gemini. Not all the way, but pretty close. Helsinki is entire words. Buenos Aires, Budapest, Amsterdam. Again, it's just doing a much better job. Now, there's some things like the Danish word for Copenhagen is, it's still limited as a vocabulary. It's only got 256,000 items, but you can kind of see that that does split up in this case. But of course, it's doing a better job than what's going on in both GPT-4 and in Mistral. So hopefully you found that benchmark useful. Again, I will make the benchmark available on my GitHub for everybody to see. But I think you get the idea. Gemini and Gemma or Google are following a completely different approach from both Mistral, Meta with Llama, and OpenAI with GPT models. I would say that both Mistral and GPT are kind of focusing heavily on getting the programming languages. I think Mistral's got a real focus on just having an efficient vocabulary based on frequency of text, 32,000 words. I think OpenAI is trying to strike a balance with a vocabulary of 100,000 and then offsetting that against the GPU costs and memory costs of running such a large vocabulary, whereas Gemini is really leaning in to people, things, cultural references, places, being more worldly, supporting different languages, different cities. So just being kind of more diverse in general. Google's really leaning into that, and where they can tokenize an entire word, they're going for it. So coming back to the original sort of stats there, 250,000 is a huge vocabulary. I think, therefore, translating that into an embeddings layer for Gemma 7b, running that as sort of 11% of your entire model is kind of massive. So, and as I said, you're trading off the contextuality and the deepness of the other layers. So its understanding is going to be a little bit less because it's put so much focus on the vocabulary, on the embeddings layer and the closeness. So there's a trade-off there. So as I said, I'm surprised that it's doing this as well as it is. But even when we come into the 2 billion parameter model, that is impressive because 25% of that entire model is taken up with that embeddings layer. But again, because it's sharing a tokenizer with Gemini, I can start to see that when you scale that up into the scale that Gemini might be, and I don't know what size it is, but if that's something like a 200 odd billion parameter model, then that embeddings layer is going to be minuscule in comparison, and therefore the context and all the other dimensions and the layers above, it's really going to help because it's got entire tokens to deal with, and it's got the cultural references and handling different languages. So again, completely different approach. I'm not sure on the whole sort of, having entire words for regular movie stars and Hollywood stars and all that, because those folks will come and go over time. But I understand why they would have wanted to do that. But you can see in the training that they haven't just run frequent text and tried to get, like a Mistral has done, and then just get the most frequently used subwords. And I would even say GPT has done the same there. Gemma has been really, and Gemini have been really deliberate in how they've generated their vocabulary. They have put in pop stars, they have put in cities, they put preferences over that. It's not a single corpus they're using. They are using maybe something similar to what I've created there and done a frequency words and then merged the whole thing together. But there is definitely a focus on things like emojis, cultural references, cities, locations, etc. And I think when we discuss this on the embeddings video, which will be one of the next videos, you're going to see why that's going to pay off, because I think you're going to have a much firmer embeddings layer. You're going to have much closeness to those tokens, and therefore with a really good embeddings layer, I think that's helping on the deeper layers kind of later on as well. But again, that's probably for another video to discuss. But anyway, hopefully that's given a bit of an insight into the Gemini tokenizer, and I'll catch you on the next video.